we'll now turn our attention to a slightly different formalism from quantum mechanics than the wave function formalism, although it's related to it. And that's a formalism that was introduced by Dirac and utilizes his Brocket notation. Uh, this formalism really is necessary in lots of research applications in which just to read the papers, they will generally do it in this. It's well worth learning in that the notation facilitates a lot of things once you get used to it and accustomed to it. It takes a little bit of effort to get your mind around the notation, but once that happens, then you find yourself using it pretty naturally. It was essentially invented by Dirac in 1926 was when the publication was. I think he did it in 25, so he was a ripe old age of about 24 when it was published, and ultimately got well, played an integral part of him getting the Nobel Prize in the early 1930s for his introduction of this Brocket notation, and then some of the calculations he was able to perform with it, and really unifying a lot of the ideas of disparate parts of quantum mechanics. It's been adopted by various disciplines outside of physics, and in particular mathematicians adopted it, and particularly their studies of Hilbert spaces and other function spaces. And electrical engineering have used it for systems analysis, so you may see it in other contexts and other applications, but a variety of areas also use this nowadays. Anytime you're doing any sort of functional analysis, it's a pretty convenient notation to adopt and to use. It's appropriate probably that the electrical engineers use it sometimes in systems analysis and signal analysis. Because Dirac himself started out, got his bachelor's degree, essentially his bachelor's degree as an electrical engineer, and then switched over to physics, and then got his PhD in physics, and essentially for this Brocket notation and some other calculations that he did with it. Dirac ultimately became the location chair of physics at Cambridge, which was the chair that Isaac Newton held back in his day. So let's describe it, maybe give a little bit of where Dirac got his insight from. Well, Dirac's insight comes really from an analogy of the wave function with a vector. And I'm kind of thinking here for the time being of the velocity vector, so I used v, but it could be any general vector. And if it's velocity, velocity can vary with time. And so it has it's parameterized by the time. And for lots of processes, it's more useful to think of the vector as a whole, as an entity in and of itself, particularly in writing the basic formula and maybe doing some preliminary calculations before you break it down into its individual components. And the velocity vector can be broken down into its x, y, and z if it's Cartesian coordinates, and usually you represent that a little more convenient. E hat 1 is is I hat, E hat 2 is J hat, etc. And so V1 is the x component of the velocity, V2 is the y component of the velocity, and so on. And one could extend this, don't have to be in a three-dimensional space. So one of the early extensions of vector analysis was to go to n-dimensional vector spaces. And so this sum here could be written like this. Vi is the component, and the unit vector here in the ith direction. To make things even a little more suggestive, one could write this not as a subscript, but just call it V of I as the component, the ith component. It's also handy to represent the vectors as either a column vector, if this had n components, an n-dimensional vector, represented as a column vector, and sometimes as a row vector. So probably have seen those in some of your classes. So there's the vector. But you can view a function, say any function, f of x, in pretty much the same way. Here I've got a continuous function, that's the line as a function of x. And I mean, it takes a little bit of manipulation in your head, but you can think of the x as labeling the components of this vector f. So here now f is the vector, I is really labeling the component. There's an infinite number of x's, so there's an infinite number of components here. But at any given one of them, the x f at xi is the value, so this f is the value up here, at the that's labeled by the component. So one can think of a function of x as a infinite dimensional vector where x labels the component, corresponding to the i's up here in these relationships, and the value f corresponds to the value of that particular component associated with the component x. Now it's an infinite dimensional, and you obviously can't write it, but if you wrote it, you could maybe think of this roughly as a column, infinite dimensional column vector. So in any event, a function, a general function, is in some sense analogous to the components of the vector. F gives the value of the component x, and so here x is labeling the component. This analogy can be extended to the representation of a vector by its Cartesian components in the following way to the wave function. Remember, we had a general wave function could be expanded on a set of orthonormal basis functions or eigenfunctions, psi1, psi2, psi3, psi4, etc. And we did this multiple times. And now you can begin to start thinking of these eigenfunctions here as more or less equivalent to these unit vectors, e1 hat, e2 hat, and the ci's here are the components, like the components of velocity up here, but the ci's are the components on this particular set of basis functions. Like up here, the vi are the components on the basis set of unit vectors. Well, we've done things like that, and so the analogy kind of extends into that. Well, to complete the analogy, Dirac looked at the scalar product of a vector, say, with itself. Doesn't have to be, but if I take the magnitude of the velocity vector v squared, it's simply v dot v, where v dot v is the scalar product. And we know how to compute that. That's just the sum of the squares of its components. We could extend that. Velocity happens to be a real vector, but one could certainly extend it to include imaginary or complex components. Sometimes it's done, particularly in other areas. And the extension of this dot product here, or the scalar product, is simply to take the complex conjugate of one of these components up here and multiply it times itself, complex conjugate times itself. And that's probably more analogous to a wave function, because we've got something really totally like it. Remember, one of the things, if I wanted to do this sum of psi star psi, which is psi squared, I'm doing a continuous sum over all of its components. Remember, the x's were analogous to the components, and the claim is that's totally analogous to the dot product for these complex vectors. I take the complex conjugate of the vector and multiply it times the vector component itself, and then add them all up. Well, here x is the component, labels the component, psi is the value. I take the complex conjugate of it, multiply it together, and then this sum is a continuous sum, so it's the integral over all of it. So these psi of x's we could generally think of as components of a vector with infinitely many components, extends over to things like the dot product and other things. Uh, in terms of matrix representation for complex vectors, we have a nice abstract vector notation that we can manipulate, and the square of it will oftentimes be written like this. This is a dagger, so v dagger dot v, and v dagger just says take the complex conjugate of each one of its values. So I've got v is v1, v2, v3. I take v1, v2, v3 complex conjugate and then take the transpose of it to get this quantity here. And then if you multiply those together, you see that you get that previous expression using the row times a column to add them up. So just standard matrix multiplication. So there's a lot of analogies between these matrices, these row and column matrices, and this wave function. And Dirac indeed proposed that more or less equivalent, that the wave function we could represent like this, just the same way that we could represent the velocity vector as a function of time. The psi labels the system we're looking at, or the wave function for the system, and it's a function of time. And he introduces this notation, which is called a ket notation to be like a vector. You can use the same notation over here, and sometimes you actually see people that instead of putting a vector sign over a vector v, they'll actually use this Dirac ket notation. So he introduces that form, and I'll introduce more of that in the next segment.